the computer sound. Okay, can you see my screen?
Yep, coming through.
All right. Okay. Okay, thanks. Thanks everybody for coming to this workshop. I'm going to talk today about neuromorphic electronics, a historical perspective and outlook. And I first want to say it's a kind of a very Caltech-centric kind of view of the field. So I apologize for those who might be left out of this presentation. And so anyway, this whole field started because there's always this natural interest in how natural systems can compute with such high energy efficiency. And so you can, 1 second, I cannot advance my slide. Patient. There we go. So it's easy enough to look at something as small as a bee to notice that you can do a lot of different behaviors that even our current flying systems such as drones cannot do without expending lots of power. And so with this kind of natural computation itself, brains can produce complex behaviors such as pattern recognition, navigation, and communication for very little power. And so, so what is the reason why brains can do this? And so we have some clues. And so if you look at the underlying architecture of brains, of human brains, you can see kind of a whole distributed system of neurons that are connected together in some unstructured way. And so the one thing that we can say is that some of this energy efficiency must come because of this distributed compute and memory type of architecture, and how we can capture this in neuromorphic systems. Now, the roots of neuromorphic computing actually come much, much earlier. Already scientists such as Turing and Rosenblatt have been thinking of architectures and also about artificial computation because they're inspired by the brain. And it was when Max Delbrück, one of the known physicists who was working in molecular biology, had challenged Carver Mead to understand whether you can actually emulate nerve channels using transistors, that I think this field kind of got started. So like the seeds of the ideas that led to kind of this whole research. And so at the time, together with two other colleagues at Caltech, Richard Feynman and John Hoffield, they started this physics of computation class. And you can read a bit more about it in this article that just came out in Nature of Electronics. And so with this kind of group coming together with ideas about how computation should work, and Richard Feynman had gone off and done quantum computing, John Hoffield came out with a whole class of neural networks, which we call Hoffield networks. And Carver went on together with John Hoffield to start this program called the Computation and Neural Systems Program at Caltech, and along also with David Winesson, and they hired the first faculty, which was Christoph Koch. And so, so a lot of the people who have worked continuously in neuromorphic engineering over the years since then really came from students, ex-students of Christoph and John Hoffield and Carver Mead. And so, so it's really, I think it's really cool that how this field has expanded over the whole world. And so if you want to know something about the history of how this program began, so click on this link later, or share the slides, and then you can see what the history of this how this program started from written by John Hoffield himself. Okay, so I want to first discuss this paper that Carver wrote back in 1990. It's called Neuromorphic Electronic Systems. It's a very lovely paper to read, and it was centered around all these ideas that were going on in his group. And the argument for why you should look at neuromorphic systems is that the energy efficiency of a computer system back in 1990 was about 10 to the power 5 ops per joule versus that of a nervous system, which is about 10 to the power 12 to 10 to the power 15 ops per joule. And so it feels that you can reduce the compute energy. And so in this case, the compute energy can be reduced by representing the information as relative values of analog signals. And that it's cheaper to do certain basic operations using analog circuits rather than digital circuits. A simple one would be like summing. And so from this, the group had built bio-inspired systems, example, the retina, the cochlea, pattern generators, local learning circuits, and so on. And so now we come to present day 2020. And I think some of these ideas are still there, but of course the digital circuits haven't really totally disappeared. In fact, they're still very prevalent. But I think the key thing that, that still carries through to today is that these neuromorphic systems use organizing principles in the brain. So for example, adaptation, learning, ideas of nonlinear amplification. And so this is why this field has grown much more than what it was back then. And so I start with a very simple, with a very basic idea of electrical signaling in the nerve membranes. And so at the time, if you look at how you would want to emulate the signaling in a nerve channel with a transistor. So first of all, the signaling in a nerve membrane happens by the flow of ions through these channels. And these channels open up more and more as the voltage across the membrane increases. And so if you look at the conductance versus the voltage across the membrane, you can see it has this exponential transfer function. Now, transistor has a very similar kind of feeling. So with the channels opening up, you get a flow of ions from one side to the other. And so for transistor, it's kind of the same thing. So you have a source of carriers, in this case, electrons or holes. And these electrons and holes will flow to the other side, to the drain side. And the amount of flow depends on the voltage that you apply to the gate. And so now if you plot the transfer function of the current flow as a function of the gate to source voltage, then you see an exponential region over here, right? Where it's very similar to kind of the exponential behavior that you see in of the conductance in nerve channels. Okay, and so this is where you want to operate your transistors in this analog domain. It's subthreshold. Turns out it's also lower current, so you get kind of the lower power consumption along with it. And so I'm going to talk about two different types of sensors and also about neurons. So I started talking about retinas because they were kind of one of the very first things that were built in Carver Mead's lab. And so everybody's known about Misha Mahawal's retina. In fact, you'll hear a bit more about it later. And so this retina has captured some of the functionality of the cells in the different layers of the retina. In this case, it's the spatial temporal filtering. And so you can model this by having resistive networks. And this is what she did through these circuits. And you can see a nice picture of the output of this particular retina sensor. Then there's also a very simple circuit from Toby Delbruck. And this was a model of the rods and cones in the retina. And here is the amazing capability of the retina to adapt over a huge order of changes in background illumination. And so this is what the circuit captures. And you can go to a much more complex model. And this is what Bernard Bohan did together with his students. And they built the functionality of these different cells that you see here very faithfully in this new retina sensor. And so it really, it was really a lovely time because you can build as complex a model as you want, right? Depending on your interest in the neuroscience. Now, the only thing is that when it comes to actually having large arrays of this, then you have to take other things into consideration. So if you have something that's very complex, you're going to need a lot of transistors, which means that you're going to get fewer pixels per unit area that you choose. And so for this, because at the time also, when this whole work was going on, Ari Fossum at JPL was building the APS sensor pixel for this CMOS sensors that are also very prevalent nowadays. And these pixels are very tiny, which means that they can put lots of pixels, right, in a particular area. And so for this, so what really the parts of the retina that stayed within the silicon retina became something which nowadays we know as the dynamic vision sensor, or DVS. And so it has just a very simple functionality. It has the photoreceptor at the front end. It's got a change amplifier that models the bipolar cells. And then it's got a threshold comparator circuit that models the ganglion cells that produces the spikes. They go out the retina. And you're going to hear much more about this in the tutorial that Toby will be giving later on this week, watching the recording. Okay, and you can see the output of this retina is much different from having an image sensor because you don't take pictures. What happens instead is if you have a rotating dot stimulus, all you're going to see is a stream of spikes, right, that represent the position, the pixel position that sees the brightness change at a particular moment. And so because the dot is rotating, you see a helix that emerges in time. So now just briefly talk about scaling. So let's see how this retina pixels have shrunk over the years, because we know there's Moore's law. So if a pixel built back in 1990 in Mahalal's retina was 100 by 100 microns, well, what is it nowadays? Is it going to be as competitive as CMOS sensors, right? And so you see a bunch of dots over here. And this indicates how the CMOS scaling has helped to reduce the size of the pixel, right? And so now the smallest CVS pixel is actually around here. It's around 5 micron, whereas the pixel size in your CMOS, in your smartphone cameras, it's around 1 micron, right? So it gives you an idea of the difference in the pixel size between these two kinds of sensor pixels. Right? Probably the reason for the bigger size is because you can see there's different transistors that you have to use in order to carry out the functionality that you're looking for, where you're looking for brightness changes. Okay, now the spiking silicon cochlea also has its own history. So the very first electronic model of the cochlea was done by Dick Lai and Carl Mead back in the 80s. And this cochlea that I show here with the layout, it's actually from the 480 tap or 480 channel cochlea. While the most current cochlea system is called the dynamic audio sensor. It's a binaural cochlea with only 64 frequency channels from 20 hertz to 20 kilohertz. And it also has this asynchronous output called AER, which I'll talk about in a couple of slides later. And it dissipates very little power, so only about 55 microwatts. And what you get from this sensor is, if you look at the y-axis, which are the channels that are sensitive for different frequencies. Now, if I play someone speaking, for example, you see a stream of spikes that come out. And whenever you have no sound, then you don't see any spikes at all, right? So in some sense, it's capturing the sparsity of events in the world. And so what's the difference between the cochlea that was built in 1988 versus the current one that we have? Well, first there's a change in technology, CMOS scaling. So we have 2 micron versus 0.18 micron technology. The power supplies can be lower now, so you're going from 2 volts down to 0.5 volts, so it actually helps in reducing the power consumption of the chip. And then also there are better circuits that people have come up for better power efficiency, for dealing with the mismatch that you get with analog circuits. And then also it has this AER output, which is, you'll see it's very useful for putting a bunch of chips together to form a system. Okay, so I'm not going to talk about all the other systems that have been built within the group and also in other groups, in Christoph Koch's group, also Paul Mueller's group at the University of Pennsylvania, who've also been working on neuromorphic circuits. But basically it led to kind of like this dictionary of neuromorphic circuit primitive. And so you can see that you could have simple circuits like similarity bump circuits. You can have a winner-take-all circuit, which you can see it's only about 3 transistors per cell. Nonlinear resistors, resistive fuse, temporal derivative circuits, adaptive filters, phototransduction circuits, current biasing. So basically it's like a dictionary that you can use, that if you think of the functionality of a particular system and you know what function you need, you can kind of put the circuits together, a bit like a Lego block, Lego kit, I should say. So of course, it's very important to talk about neuron models because these are the basis of all the neural processors, right, for neuromorphic engineering. And so again, there's a whole level of complexity that you can build into your pixel. You can have a very simple neural model, integrated file model, also we call it axon hillock circuit, where the current coming in, say from the synapse, would charge up the membrane of the neuron. And then if it exceeds the threshold, then you put out a digital spike, and then you come back and you reset the membrane. And you see this down the curves below. So with the green curve, you can see the charging of the membrane, the creation of the spike or the event, and then the discharge of the membrane, and then the charging up again if the current stays, right? And then what you would output are these pulses or spikes. Now you can make the neuron model much more complex if you want to capture the different firing properties of neurons that you see in the brain. So if you want to say capture a regular firing neuron, fast spiking neuron, etc., then there's a particular model called the Zickovich model, where there's a set of dynamical equations, and then you can build these equations into your transistors, okay? And so you can see the number of transistors now grows. There's also this DPI neuron where you would have the transistors to emulate the dynamics of the conductances like sodium, potassium, the leak of the neuron, NMDA synapse, and so on. So this is from Giacomo Indivieri. And so you can see that now you have even more transistors. So basically which circuit you use really depends on your interest of what you would like to use this chip for, okay? And so there's a paper that you can read where you can see this whole zoology of neuron circuits. Now the DPI neuron has been put together into an array of 256 neurons, 128,000 synapses, along with analog plastic synapses. So synapses that have short-term plasticity and also long-term plasticity, learning synapses. And you have also a NeuroGrid, which came from Cavea Bohan's lab. And you can see there, because they included a lot of the details of the neurons, each neuron uses 337 transistors. And if you now have a chip, which is, I think, about 15 by 15 millimeter on the side, then you put 65,000 neurons. Now you can take each chip and then, make a whole array of them, and you can get to your 1 million neurons, right? Because the target back then was to hit the 1 million neurons. And so the lovely thing about this is you can see that this whole system runs in real time and only burns 3 watts, right? And so basically the systems are built because now you can actually test out some of the neuroscience models that were running around at the time, right? And to see how effective these models are. And in fact, there's another project called the Brain Skills Project. So now in this project, you can actually implement up to 3.9 million neurons with 880 million synapses. So these are large numbers, right? And you have to use 20 wafer modules to get this whole array of numbers. But they're really good for people who want to do large-scale simulations of spiking neurons because it's very slow to run on a computer, right? So that's what this system, this particular system is useful for. Now, the thing to remember is that we don't always have to build everything out of analog. In fact, people are also building what we call time multiplex digital neuron hardware accelerators. And so you can even use a commodity port like an FPGA to implement 1 million neurons in a multiplexing manner. And so this was actually done by Andrew Cassidy and Andreas' group, who showed that this was possible without building actually a custom chip. And then of course there are other chips that came along that really custom chips that really implemented kind of the same idea, which is this time multiplex digital system that will compute all these neurons. And they're able to do this because silicon is very fast, right? And so Spinnaker, for example, is an ARM-based core where you can implement up to 16,000 neurons per core, burns a watt. You have plastic synapses. IBM TrueNorth is another one that I'm sure many of you have heard of. Again, uses both synchronous and asynchronous digital circuits, burns only 7.3 milliwatts, so it's kind of low power. And Intel Lohi, this is the kind of the most current spiking network chip. And you're gonna hear more about this on Friday from Mike Davis about this particular system. And it's programmable. You can program different synaptic learning rules, dendritic delays, and so on. Okay. And so you can see there's an array of hardware you can use to try out different ideas about how network architectures can give you interesting types of computation. And so I want to also talk about Cavea. So Cavea was a project, was a European level project which brought together different partners, also where DVS comes from. And so you can see that now if you have these different chips, you might want to put them together. Well, how are they going to talk to each other, right? Because we don't have a clock system. The information is transmitted via this asynchronous events. And so in Cavea, we have the input from the silicon retina coming out. So in this case, looking at a ball or circle. And now the spikes are then transmitted to a set of convolution chips. And then transmitted onwards to what we call an object chip that looks for the best template that matches what you see in the scene. And then also a learning system that has to learn spatial temperature trajectories about the object. And so you can see this was back in 2006. And so you can see the boards are very big. kind of unwieldy, but still you can see the functionality of this completely hardware AUR system. Right? And so I'm going to play a little bit about
in each of the displays,
output.
we see the events coming out of a particular Cavea component. In the first one, we see the events coming from the temporal contrast retina, where we can see the events coming from the stimulus, which are the large circle and the small circles going around and around. Those, the output of this is going to the convolution chips, and the convolution chips only produce output for the large circle. It's not a clean output, but centered in the large circle that's going around, and we don't see the small circle. That output from the convolution chip goes to the winner-take-all chip, where we just have output for the center of the large circle. We don't have anything else in our output. We only see these events. And this output from the winner-take-all is used to stabilize electronically the output of the retina. So now we see the same output we had from the retina, but centered in the large circle.
Okay. So it gives you an idea of the kind of output responses that you get from such a system. Now they're displayed as frames, but really these are asynchronous events that are flowing through the system. The next thing.
In each of the displays.
Okay, so I kept on talking about AER. So what is AER? So AER stands for Address Event Representation. And so the way that we do the wiring, because wiring is expensive, is that we do virtual wiring through AER. And so each of these chips have neurons on the output. And what these neurons do is they will spike whenever that particular channel or neuron is active. And so these events or the spikes are marked by their addresses, right? And so in this case, you can see neuron number 2 spiked first, followed by neuron number 3 and 1 around the same time in 2. And so basically you get this asynchronous stream of spikes coming out, and then you can send them onto another chip, which acts as a receiver that now has to decode these addresses and to drive the neurons in now the receiving chip. And so there's a whole lot of work that gone into creating this asynchronous representation protocol so that it runs correctly. And so if you're interested in kind of the circuits of that carry out this this protocol, you can look at this seminal papers from Cavea back in 2004. And of course, this whole AER connectivity scheme has improved tremendously also over the years. Okay, so what sort of neuroscience primitives can we implement now on this spiking neural network chips, right? So one thing we can do is to look at the anatomical organization of the neurons in a piece of cortex, and then come up with a very simple model. And this is what Ronnie Douglas and Kevin Martin did early on, or late on in the 80s. And so what you can do is you can kind of simplify this idea of how the cortex works, even though the neurons look very different. And basically they boil it down to 3 blocks, right? So you have 2 blocks. There are the blocks for the excitatory cells. So remember, there are 80% more excitatory cells. No, there are 80% excitatory cells and 20% inhibitory cells in the cortex. And so basically these 2 blocks here represent excitatory neurons in different layers. And then you have another block for the inhibitory cells. And so one thing you can see between these 3 blocks, you have connections between each other and also to yourself, right? So you have your own self-recurrence. You also have excitation on each other, and also the inhibitory population, or this block here now inhibits the excitatory population. And also you get the input, in this case from the thalamus, which weakly drives these blocks here. And so now this is a very nice sort of model where you can now create a motif, and I spoke about this also earlier, and this motif is a winner-take-all circuit, right, which does some nonlinear amplification. And so now this excitatory neurons, which are represented here, drive inhibitory neuron, and this inhibitory neuron goes back and inhibits the excitatory neurons. Okay, so this is a motif that's carried on again and again in different neuromorphic chips. And then the other model that was that's interesting that came out of this kind of organization is what we call the reservoir networks. And so there are 2 different ones that came out quite some years back, and this is the liquid state machine and the echo state networks. The liquid state machine has this distribution of excitatory and inhibitory neurons. and also has these connections between the two populations. And it's been used for learning spatial temporal trajectories, well, actually temporal trajectories. So in this case, you can think of this as a whole dynamical system. And so when you present inputs, say from a spiking sensor, then what you want to learn is to learn the inputs from the neurons in the pool that would help you solve a problem, okay? And so you can hear more about this maybe, but Wolfgang Maas will be talking on Thursday, so do come and listen to his lecture. Okay, so I want to briefly talk about mismatch, right? Because these are analog circuits and we have to work with analog circuit mismatch. And so what is this mismatch? So here we have a photoreceptor circuit. And so now if I look at the just a single transistor and I measure the IV curve, the current versus voltage curve of this one transistor, you've seen it before. You see this subthreshold region and then above threshold region. Now, if I take this pixel and I make multiple copies of it because I want to have an array of such pixels, then do we expect to see the same curve again? Well, because of transistor manufacturing reasons, you actually have fluctuations in the dopants underlying the channel of a transistor. And because of this, instead of getting this one curve overlapping on top of each other for, say, 300 transistors, you actually get a whole set of curves, and you can see the spread in the current versus voltage transfer function. So basically, there's a variance, right, between the measurements of different transistors from the different pixels. And because of this, when you work with these neuromorphic circuits that have analog transistors, then you have to worry about mismatch, right? And there are ways to get around it. And so even in this Cavea system that I just showed, we had to get around this. And so Toby Delbruck will talk about one of the ways that you can do this within the DBS pixel. And so you can hear more about it in this tutorial. Okay, so I want to now switch to talking about deep learning artificial intelligence, because there was another kind of hardware that came along also probably 10 years ago. These are the GPU cards that are used by people who game a lot. And it turns out that these GPU cards are really useful also for training these networks that have already been proposed back in the 60s, convolutional networks, recurrent neural networks. And so the training of these networks was impossible back then, but with this GPU cards, you could actually train now these networks. And nowadays, these are the networks that produce state-of-the-art results in many different fields like speech recognition, natural language processing, and so on. Now, if you again worry about power or energy efficiency, then you can see for two different types of networks. So this is a convolutional network, and this is a recurrent network architecture. Is that if you run it on a GPU and compare it to running again on an FPGA, another commodity part that's become very useful, then you can see that you can actually get over 11,000x in energy efficiency, right? So it suggests that we can actually, if you're interested in low latency, high energy efficient hardware systems, the FPGA could be a useful platform for us to investigate different types of network architectures. Now, one thing with either an ASIC chip that you build or even one of these FPGA systems is that usually the chip is partitioned such that you have processing element blocks and then you have some bit of on-chip memory, but most of your memory is actually off-chip. And it's usually in DRAM because it's cheap, and also you can get very high density memory from the DRAM. And so let me just show you where actually this most of the memory consumption comes from when you run a network such as this. So this is the analog neural network where we're now going to first fetch the activations. And usually you can either store this on SRAM or DRAM. It really depends on the architecture that you're running. And then you have to fetch the weights, right? Again, in this case, we started in DRAM, so now we have to fetch it from DRAM. And once you've had the weights and the activations in the processing element, then it does the summation, the sigmoid, and then you get the value of this for the activation of this neuron, right? But the thing is, people worry a lot usually about the energy in the processing element, but actually the energy that you consume mostly comes from fetching the information from these different pieces of memory. So if you fetch from SRAM, it's 10x more than the energy of the processing element, but if you fetch it from DRAM, then it's 1000x more. And so you can increase the energy efficiency of the network by exploiting spatial and temporal sparsity, and by training also now the networks with so that they have sparse weights and also low bit precision parameters. And so this networks have become very interesting because instead of just updating all the neurons all the time, right, and fetching the weights from memory when you need to update the next layer, you can now think of using neuromorphic ideas, thinking of spiking networks where you do it in a data-driven manner, where you find conditions where certain neurons only need to update the neurons in the upper layer, right? And so with this, you can reduce the cost in fetching the weights from memory. And so this is something that we're using also in a system for continuous digit recognition. And so quickly here, so we have now audio sensor, dynamic audio sensor where you can get frame features that you now drive what we call a delta recurrent neural network based on this different data-driven idea that we've talked about. You can put it on an FPGA board. And now if you look at the energy efficiency for this particular digit recognition task, we're at 10 to 9 ops per joule. And then if you now compare it with the numbers that we have for what we got for computer system level back in 1990, you can see the energy efficiency has increased by 10,000, 40,000, right? So this is partially due to Moore's law and partially due to an understanding of how you should set up the architecture so you don't do computes all the time. Okay, so I have a couple more slides about non-volatile memory technology, which I think I'm going to skip over because of interest of time. I'm going to just briefly talk about this, just this one picture here. So now, so I haven't talked about learning and memory. So to do local learning and memory, you want to have basically your memory close to your logic, right? So this is based also on the calculations that we had in the slide before, where fetching things from memory is expensive. So if you can put memory local to the computation, then you can actually save in your memory consumption. And in recent years, there have been a number of interesting memory devices, non-volatile memory devices that have come up. So these are like resistive RAMs, phase change memory, MRAM. And if you embed now this along with charge-based memory like SRAM, DRAM, and flash within the pixel, and you do computing within the memory. So you don't, so basically here's the logic. And so usually what you do is the control unit will fetch the values from memory and then give it to the logic unit then puts it back again after it's computed on the information. But here you can actually try to do the computing within the memory. So basically you're going to increase the energy efficiency of this new type of systems. And so these are going to be very interesting in the next few years. And so you can read a very nice article in Nature Electronics that came out also this year. And so what's the future like? So future is going to be actually very interesting, very exciting, because we have emerging transistor and memory technology, higher energy efficient hardware architectures that many people are thinking about in the neuromorphic side and also in the deep learning side. We're going to be investigating algorithms for continual adaptation and local learning. So there's something of interest in many areas. And also ideas, new ideas for event-based asynchronous signal processing. And the application domains are in edge computing devices, example, event camera, and the Cochlea can be used for auditory signal analysis, video monitoring, human-machine interface. That's for mobile wearable electronics, fast robotics. Here's a nice little video, EV Dodgenet that you guys should look up on YouTube. It's a drone carrying an event camera trying to dodge a basketball. Okay, and also other places are neuroprostheses. And so in conclusion, I'd like to thank the colleagues from Cavea Meets Group, also from Caltech, also the colleagues over the years from all the different Telluride Neuromorphic Cognition workshops They've discussed a lot of these ideas. Colleagues over at Institute of Neuroinformatics, also from our census group, and the National Science Foundation and other commercial companies that have sponsored the workshop. And also thanks to all for you for listening.
Great.
Oh, and one last thing. If you're interested in reading, there's a whole set of books that you could read if you're a beginner to this area. So there's a bunch of textbooks that you can start from. Because all this information, gets old very quickly. So the newest one is also already back in 2015. Okay.
Thanks, Shih-Chii. And yeah, this is great. I think one thing that's exciting about today's talk slate is that they're all by people who have literally written the textbook in each of these respective areas. So that was fantastic. I really appreciate the perspective on the history, especially of hardware. And one of the really exciting things about this workshop is that we also have a broad, set of contributions from people, not only hardware, not only machine learning, but obviously computational neuroscience as a first-class citizen of our of this workshop as well. And there's probably no better way than to demonstrate this than to introduce our next speaker, Terry Sinowski, who is probably the most well-known computational neuroscientist in the world, certainly one of the most cited.